Okay, so this is the story of one of the most ingenious computers ever created and how its fault-tolerant design helped save Apollo 11. July the 20th, 1969. Neil Armstrong and Buzz Aldrin were in the lunar module 40,000 feet above the moon's surface and descending rapidly. All seemed to be going well when suddenly the onboard computer flashed a 12:02 program alarm and the computer restarted. Neil Armstrong, as ever, remained cool, calm and collected and radioed Houston with just a hint of urgency in his voice, asking for a status on this very serious program alarm. 3 nail-biting seconds later, Houston came back and gave Armstrong the go to continue. And they continued towards the moon. Suddenly, another program alarm occurred, and another, and another, and another. In total, there were 5 program alarms and restarts during the Apollo 11 landing, the last one just 2,000 feet above the moon's surface. There could not be a worse time in the flight to be having computer problems. At the time, the media gleefully reported how Armstrong seized manual control from a crippled and failing onboard computer and managed to heroically and single-handedly land the spaceship on the moon with program alarms and malfunctions flashing all around him. Nothing could be further from the truth. Neil Armstrong and Buzz Aldrin were outstanding pilots, but the Apollo guidance computer worked flawlessly in this mission and every other mission that it flew. And this was thanks to pioneering hardware and software design principles that were used to make the system robust against any failure and which form the foundation of all sorts of robust systems today. So this talk over the next hour is split into 4 equal sections. First, I'm going to introduce you to this amazing machine. Then I'm going to walk you through step by step how the computer landed the astronauts on the moon. Next is the sort of technical bit, and I'll talk a bit about how the software was made robust and some of those pioneering design principles. And finally, we'll jump back into the cockpit. We'll go over the Apollo 11 landing and we'll get to the bottom of those program alarms. So first, let me introduce you to this machine. There it is on the slide. And it was designed at the MIT Instrumentation Laboratory. The computer was responsible for almost all of the guidance, navigation, and control of the Apollo missions. And you had the same computer on the command module, so that's the mothership, and the lunar module, that's the thing that landed on the surface of the moon. It weighed only 32 kilograms, consumed only 55 watts, and occupied only 1 cubic foot of space. Now, for those who are old enough, cast your minds back to the 1960s. If I said to you, think of a computer, I think most of you would think of an enormous mainframe filling an entire room, consuming vast amounts of power and needing huge amounts of cooling. Now, look at this slide and think again. And the computer ran at between 50 and 100,000 instructions per second, which might sound quite slow, but as you'll see later on, you can do a lot with 100,000 instructions per second. Now, the computer was built completely from scratch from one type of logic gate, the 3-input NOR gate. And this is something that often passes people by. It was literally built from nothing. And these logic gates were on integrated circuits, which again was a revolutionary decision in the early 1960s. You had 2 of these gates for each integrated circuit, so that's about 3,000 gates in total. And these gates were not soldered together, they were welded together to form modules like this one. Now, if you look on the slide, you might see some pins running along the top of that white module, and those pins are used to plug the modules into a backplane. So 26 of those modules with those 3 input NOR gates inside plugged into a backplane. The backplane connected everything together, and that formed the final computer. There's another picture of the tray with some modules inserted. And there's a picture of the backplane. And each of those little blue lines you can see is a wire connecting the pins of the different modules together. So the backplane was very complicated. Now, memory in the computer was very, very limited. It had only 2,000 words of RAM. And if you look on the slide, you should see some silver rings, and each of those silver rings, or sorry, ferrous rings, stores 1 bit of data. And then the grid of copper wires is used to select which bits of data you want and to read and write the value. So you might have seen that, but what was a bit weirder was the ROM, and this was where the program was stored. And I've shown that on the slide as well. And you can see those little wires going through those red rings. And if a wire went through a ring, that corresponded to a 1. And if it didn't, that corresponded to a 0. So the software was literally woven together to form the fixed memory. Here's one of my favorite pictures from the Apollo program. This is a worker at Raytheon, and she effectively has a binary listing of the program in front of her, and she's weaving those copper wires through those red rings to convert that program into something that will fly on the spaceship. So you really wouldn't want to make a mistake when you were doing that. The computer was very featureful, bearing in mind it was made up from only 5,500 logic gates. It had a real-time clock, interrupts, parity checking, and extensive I/O connectivity. All really good stuff. But it also had some quirks. So for the programmers amongst you, it had a 15-bit word size. Yes, hold on to your table very tightly. It used 1's complement for integers, which meant you could have 2 values of 0, positive 0 and negative 0. It had no floating point support. It just used scaled integers, although actually in many ways that's better, so that's not too bad. And the instruction set was incredibly dense, and there wasn't space for instructions for doing things like shifting values. So the computer also had various special memory locations. So for example, if you wrote a value into location 20 and you read it back again, you would get that value shifted 1 place to the right. As we've seen, the memory was incredibly limited. It had no stack, and it had an unusual and constrained instruction set that would be sort of barely recognizable to a modern day programmer. Now on to the exciting stuff, I/O. So this device, called the Disky, was the main way that the astronauts interacted with the guidance computer. And you can see it's just like your laptop. It's got a screen on the top right-hand side that can show some numbers. It's got some indicator lights on the top left, and it's got a keypad at the bottom where you can enter some data. The Disky used a verb-noun format for commands, and I'll show you that later. And there are also many other human interface devices present, such as an 8-ball, indicator lamps, and hand controllers. Of course, the computer was also able to send and receive data from Houston over the radio. And of course, if you're a computer in charge of a spaceship, you have some very exciting I/O devices like thrusters and a massive rocket engine. And I'll demonstrate all of this input-output to you later on. Okay, so that's my whistle-stop tour of the computer, and I'll very happily take more questions and delve deeper into that in the Q&A if we have time. But now I want to show you the computer being used. I want to show you the computer landing on the moon, because after all, that's what its purpose was. First, though, we're going to need a spaceship. So here is our spaceship. And the first thing we need is a big rocket engine. And we use that rocket engine to slow ourselves down and come out of orbit and gently down onto the surface. We also need to be able to steer, and that's the job of these RTS thrusters. The main source of data for the guidance computer is this contraption called the IMU. And the IMU allows the computer to calculate where it is and how fast it's going. There's also a radar that's used to measure the height of the spaceship above the moon's surface. Next, and very importantly, is the window, and I'll have a lot to say about the window later on. And finally, sitting in the middle of our spaceship is our hero, the Apollo guidance computer. And it reads data from the IMU and the radar, and it controls the thrusters and the rocket engine to bring the spacecraft gently onto the moon. I just want to talk about a couple of these things that you may be less familiar with. First are the RCS thrusters. So on the left-hand side, you can see that on the four corners of the spacecraft are these clusters of RCS thrusters. And then on the right-hand side, I've shown you one of those clusters. And you can see there's thrusters pointing up and down and outwards. And the computer can give little squirts of thrust through any of those thrusters. And by doing that, the computer can steer the spacecraft in any direction that it wants to. The other device you may not have seen is the IMU. The IMU consists of 3 concentric rings that can rotate around inside each other. And then right in the middle sits the stable member. The stable member has gyroscopes on it, and those gyroscopes keep the stable member completely fixed in space. So no matter how the spacecraft turns, the stable member in the middle stays completely fixed because of the gyroscopes. And then sensors on those 3 rings can measure how the spacecraft has turned relative to the completely fixed stable member. And then the computer, by doing some integration, can then calculate the speed and the position of the spacecraft. So the IMU was the real keystone of how you do navigation in space. Okay, so that's our spaceship. Next, I just need to spend 2 minutes giving you some essential training of how you land on the moon. And then once I've done that, I'll sort of give you the demo of the computer actually doing it. So let me set the scene for you. We're coming into the mission, and the lunar module is in what's called the descent orbit. And the descent orbit is quite misleading because the descent orbit doesn't take you down to the surface. The spaceship could quite happily whiz around this orbit forever and ever. To land on the moon, we need to perform a series of maneuvers that take us out of orbit and down onto the surface. And those maneuvers are the difficult bit of the landing, and those maneuvers is what I'm going to talk about today. And those maneuvers are split into 3 phases. The first phase is P63, the braking phase. The aim of P63 is to slow the spacecraft down. At the start of P63, we're really high and we're going really fast. And we fire that rocket engine out in front of us. And that slows us down and we lose most of our height. Then when we're about 8,000 feet above the surface, we enter P64, the approach phase. At the start of P64, the spacecraft pitches over, and that gives the astronauts a good view of where they're going to land, which is sort of useful. And during P64, the astronauts and the computer work together to fine-tune the landing site. And then finally, when we're above the landing site, we enter P66, the final phase. And the aim of P66 is to touch down nice and gently without breaking the spaceship. So those are the 3 phases of landing. And this is the one slide you need to remember. P63, where we slow down and we lose most of our height. P64, where the astronauts and the computer work together to fine-tune the landing site. And P66, where we want to touch down nice and gently without breaking the spaceship. Okay, fantastic. The training's complete. We can do the demo. Now, there's lots of details here because I really want to show off the computer to you as best as I can. Also, on the flip side, I have made some simplifications. So if anyone's an orbital mechanics genius here, don't get too annoyed. load the landing software. So they go to their diski, which you should see on the screen, and they enter verb 37. And that means, please load this program. And then they enter the program number, which is 63. And when they do that, the computer switches to program 63, just like that. And the first thing that the computer does is it flashes verb 6, noun 61. Now, the computer has been programmed with the exact landing site that they want to land at. And the computer knows where it is because it's got the IMU. And so the computer has calculated at exactly what time it needs to light the rocket engine so that we land in the right place. And that time is shown there on the diski. So we can see the computer's saying it's 10 minutes before I need to light the rocket engine. It's 10 minutes before we're due to start the landing. Let's wind forward the clock a bit. It's now 1 minute 20 before ignition, and we can see that on our diski. And the computer has an important message for the astronauts. And to signal that, it highlights the key release light on the diski. The astronauts can view that message by pressing the key release button. And the message is verb 50, noun 18. Again, don't worry about the details, just get a flavour for what the astronauts are doing. So what does verb 50, noun 18 mean? Well, the computer is asking permission to maneuver the spacecraft so it's pointing the right way. And if the astronauts are happy with that, they press the proceed key at the bottom there. And then the computer will automatically maneuver the spacecraft so that that rocket engine is pointing out in front of it. It then does a little burn to make sure that the rocket fuel is settled in the bottom of the fuel tanks. And we're now ready to go. So let's wind forward the clock again. It's now 5 seconds before ignition. Are you excited? I'm definitely excited. And the computer flashes verb 99, noun 62. Now, every Apollo astronaut can tell you what verb 99, noun 62 means. It means, are you sure you want to land on the moon? And the astronauts have 5 seconds to calmly reach over, press that proceed key on the diski, and secure their place in history. So just to remind you, this is where we are. We're in our descent orbit, but now it's exactly the right time to light the rocket engine. And we know how this works. It starts with P63. And the first thing that happens is the biggest anticlimax in spacecraft history. The computer lights that rocket engine at a barely noticeable 10% thrust. 10% thrust is not going to do anything to land you on the moon. So what is the computer up to? Well, it's measuring very carefully to see if that thrust causes the spaceship to spin around. And if the computer detects a spin, it will swivel that rocket engine to make sure that the thrust is acting through the center of gravity, and that will stop the spacecraft spinning around. So for about half a minute, the computer sort of very carefully lights the rocket engine and very carefully swivels it to make sure that the thrust isn't causing the spacecraft to whiz around. And once the computer is happy, it ramps up the thrust. And for reasons I won't go into here, full thrust is 94%. Okay. Now, this is not just a case of fire a big rocket engine and hope for the best. Throughout the entire landing and this entire demo, the computer is running sophisticated algorithms. Those algorithms have 2 points in mind at all times. The first one in green is the desired landing site. I've shown that at the bottom of the slide. Hopefully you can see it. The desired landing site is where you're telling the computer you want to land. And the other one in blue is the projected landing site. That's where the computer thinks it's going to land based on extrapolating its current trajectory. And the computer's main aim for the entire landing is to steer the spacecraft to try and move that projected landing site towards the desired landing site. Now, at the start of P63, the landing radar can't see the surface, so the only source of data for the computer is the IMU. Now, the IMU is incredibly accurate, but it loses accuracy during accelerated flight. And of course, nothing says accelerated flight like having a big rocket engine lit up in front of you. So the computer signals that it doesn't know exactly how high it is or how fast it's going by lighting those two lights on the disky. Okay, great. Now we're still in P63, but we're a bit lower. We're now 40,000 feet above the surface, and the landing radar now locks onto the surface and it starts providing height information to the computer. So there's the situation we were in. And then when the landing radar locks on, the computer clears those two lights from the disky because the computer now has a much better idea of how high it is and what the rate of descent is. Now the astronauts are waiting for this moment. And when it happens, when those lights go out, the astronauts enter verb 6, noun 63. And that means, please show me the discrepancy between how high you thought you were before the radar locked on, and then how high you actually are now that the radar has locked on. And the computer replies, and the number we most care about is that discrepancy, which is the top number. And we can see here the computer saying that there's 1,000 feet discrepancy between where it thought it was and where it actually is now that the radar is locked on. Now the astronauts sort of check this information, and then when they're happy, they enter verb 57. And that tells the computer to incorporate the landing radar data into those guidance calculations. And then the computer will gradually correct the trajectory based on this new information. So just kind of seeing what that looks like outside the cockpit. So the landing radar locks on. That has the effect of moving the projected landing site because the computer's in a different place to where it thought it was. And then, as always, the computer will steer the spacecraft to move that new projected landing site back towards where it wants to land. Okay, lovely. Towards the end of P63, we ramp the thrust down, and then we enter P64. Now, we're about halfway through the landing, so stick with me. Now, if you remember, at the start of P64, we need to tilt the spacecraft over so that the astronauts have a good view of where they're going. And then if you remember, the aim of P64 is for the astronauts and the computer to work together to fine-tune that landing site. So how does that work? Well, the computer needs a way of telling the astronauts where they're going to land. It's the most primitive device on the spaceship. It's the window. And the window has two axes on it like this. And throughout P64, the computer shows verb 6, noun 64. And let me just show you how this works, because I think this is such a simple solution to a difficult problem. If you look at that 5 on the disky, that means look 5 along the horizontal axis. And then that 40 means look 40 up the vertical axis. And then you imagine a red dot on the window. And that red dot is the computer telling you where you're going to land. So using that information from the disky, Armstrong could look out the window, he could imagine that red dot, and that would be the computer saying that is exactly where you're going to land. But what happens if Armstrong doesn't like the look of the landing site? Well, he's got a hand controller. And if he moves his hand controller, that moves the desired landing site. So there's where we were. And then if he moves his hand controller, that moves the landing site. And then, as always, the computer sort of sighs and crosses its arms and says, okay then, and it re-steers the spacecraft to move that projected landing site towards the new desired landing site. And it was common throughout Program 64 for that imaginary red dot to move around the window, particularly if Armstrong was changing the landing site with his hand controller. Now let's just look at how the software works during Program 64. So that the hand controller feeds into those sophisticated guidance algorithms. The hand controller changes the desired landing site. And then the guidance algorithms calculate how the spacecraft should be steered to reach that landing site. And those steering commands go into the low-level steering software. And that low-level steering software then calculates which thrusters should be fired to steer the spacecraft in the right direction. Now, once we're above the landing site, we move that pings mode switch from auto to attitude hold, and that puts the computer into Program 66. So we're above the landing site, we've moved that switch, we've entered Program 66. At which point the hand controller is disconnected from those sophisticated algorithms and it's connected to the much lower level steering software. And that means in Program 66, when Armstrong moves his hand controller, that directly steers the spacecraft. So if you remember in Program 64, when he moves his hand controller, that moves the desired landing site. But in Program 66, it directly steers the spacecraft. So it's a much more direct relationship of control. But I want to make the point that there is software running between the hand controller and the thrusters at all times. Finally, when we're just above the landing site, a big cloud of smoke and dust gets kicked up and the astronauts can no longer see out the window. So they look inside the cockpit at two instruments, both controlled by the computer. The one on the left, called the 8-ball, that tells you whether you're pointing upwards or whether you're about to fall over. And the one on the right tells you whether you've got any side-to-side movement. And so the astronauts would look at these two instruments, and they'd carefully steer the spacecraft to make sure they land the right way up and nice and carefully. Once the spacecraft touches the ground, a blue light illuminates, probably the best light you could ever see if you're an astronaut, and you very quickly shut down the engine, breathe a big sigh of relief. And that's how you land on the moon, and that's my demonstration of the Apollo guidance computer. However, what about those pesky program alarms? They were not supposed to happen. Now, a 1202 is a very serious alarm. In modern day terms, it's a bit like seeing that on your onboard computer. Or if you're a bit more old school, something like that. Or possibly, worst of all, that. A 1202 alarm was a serious problem, and the astronauts and Houston had to very quickly make a decision about whether it was safe to continue or whether they should abort the landing. And that decision is the subject of the second half of my talk. And that's split into two parts. First, I'll talk a bit about how the software was made robust, and then I'll give you another demo of what happened on Apollo 11, and I'll show you how the computer played its part in saving the mission. First, though, let me talk a bit about the software. Now, the software that was on the spacecraft was very sophisticated. I hope that my demo has kind of persuaded you of that it wasn't just a case of fire a rocket engine and hope for the best. The software controlled all phases of the lunar module's mission, and it manipulated the thrusters to steer the spacecraft. It updated the diski with the information that the astronauts could see. It was controlling those instruments in the display in the cockpit, like the 8-ball. It was sending the telemetry back to Houston. And so it ran a very simple real-time operating system that they wrote from scratch. And as always, the source code for Luminary is available on GitHub. Good luck trying to run it. Now, the software, I've picked out 6 design principles that were used to make the software robust. Now, some of this stuff might sound obvious to you now, but back in the 60s, it wasn't obvious that this is how you make software robust. And it was thanks to the usage of these principles on things like Apollo that this kind of sort of got bedded in as the way that you write reliable software. So 6 principles, off we go. Number 1, use a high-level language. So I hinted earlier that the computer's assembly language was very primitive. There were no compilers or anything like that. You just programmed in assembly language, and this made it hard because you have these complex guidance algorithms that you then have to translate into this really sort of twisted and contorted assembly language. And also 15-bit integers means that the numbers you can store are not particularly big, and that doesn't give you the accuracy that you need for guidance calculations. So perhaps more colloquially, for those sort of less familiar, the computer could only represent numbers to about 3 decimal places, and 3 decimal places isn't enough accuracy if you're doing these calculations and you want to land in exactly the right place. You sort of want more decimal places. So their solution to this was they wrote something called the interpreter, and this gave you a sort of a virtual assembly language on top. And the instructions for this were a lot more sophisticated, and they gave you things like matrix and vector operations, which are really handy if you're doing physics calculations. It gave you such luxuries as being able to index into an array, and it gave you a stack, and the stack is really useful for manipulating values. I don't know if anyone's used those old HP calculators with the reverse Polish notation, but anyone who has will know that having a stack to kind of store temporary data is really useful. The interpreter also gave you double and triple precision integers, so it gave you more decimal places in your calculations. And it had various other benefits, but the main downside was that interpreted code ran really slowly. So the final system was a compromise between the two things. The sophisticated guidance algorithms that would run once every couple of seconds were written in the interpreter, and that was a great fit for those. And then the really time critical stuff, like the software that controlled the thrusters to steer the spacecraft, that was written in the low level assembly language. And so the final system was a hybrid of these two approaches. Number 2, divide your system into jobs. So the software was sort of seemingly doing lots of different things all at the same time, and the system was divided into jobs. For example, there was a job called readax, which read data from the IMU and calculated where the spacecraft was. There was a big job that was used to implement the digital autopilot. That's basically the thing I demoed to you earlier. There was a charmingly named job called Pinball, and Pinball would update the displays on the disky for the astronauts, etc., etc. Each job had a small area of memory where it could store temporary information. So that's like having a piece of paper where you can sort of show you're working when you're doing some calculations. And there was enough memory to have 7 jobs on the go at any one time. Number 3, restart on failure. Now, it's a sad fact of life that all software will encounter failures. Now, this is quite nuanced. I'm not talking about bugs where the programmer was lazy or they misunderstood the specification. Those sorts of things would be found during the testing phases of the project. The failures I'm talking about are things that happen, once in a blue moon, 1 in a million. You never see these things happen during testing, but you see them in the real world. And these really rare events can trigger unusual flows through your code that can cause your software to fail because you sort of didn't think of that scenario. Now, if software has failed, it can't be trusted to recover itself. It's got itself into an unknown state. So instead, you restart the software. And this is that sort of old joke where if your computer breaks, people say, well, switch it off and switch it on again. But it really works. When you restart software, if something unusual happened that caused it to fail, when you restart, the software can sort of have another go at running, and hopefully that transient condition has gone away. And restarting was so core to the guidance computer that it gave you all sorts of different levels of restart. You could sort of restart everything or just a little bit. Restarting was really essential to the software. Okay, we're halfway through, and thanks for bearing with me. Number 4, checkpoint your good state. So restarting is great, but if you haven't saved your work, you have to start from the beginning. So the solution for this is when your job reaches a known good state, you save that state for later. And then if you get restarted, you can read back in what you saved and you can pick up where you left off. For example, if you're the read apps job and you're reading data from the IMU and you're doing loads of calculations, and then at the end of the calculations, you get a new answer for where the spacecraft is. Once you get that new answer, you save it so that if you get restarted later, you can kind of see what the answer was before. But if you crash halfway through the calculations, you don't touch what you saved. Number 5, hardware monitors the software. So this is sort of the most fiendishly technical of all the slides. So the computer had all these different jobs, and it used something called cooperative multitasking. And you can think of this is sort of like the most polite software you can ever think of. So if you're a job and you're involved in cooperative multitasking, then every so often you look around and you say, would anyone else like to run? Would anyone else like a go at running on the computer? And if another job sort of says, yes, I'm waiting to run, then you sort of step back and you let the job that's waiting to run. But what's really important is it relies on people writing their code so that it's really polite, and every so often it checks to see if there's another job waiting to run. And the way this works technically is your code every so often has to check a special variable called new job. And if there's a particular value in that variable, then you have to give up control and you have to hand over to whoever's waiting. Now you might say, well, this all sounds a bit rubbish, because what happens if you get a job that isn't polite and sort of doesn't ask if anyone else is sort of waiting? And don't you think, by the way, in real life, it's really annoying when everyone's being polite and then one person just kind of steamrollers in and sort of doesn't go along with things? It's really annoying. However, the software was all written by one team, and so they all made sure that the code they wrote was polite. But you still might get some, situation where, for whatever reason, like a job might get into an infinite loop and sort of forget to see if anyone else is waiting. And so the hardware actually sort of monitors this. And if new job hasn't been checked for a certain amount of time, the hardware will trigger a restart. So you could think of that as everyone being polite, but there's sort of like a security guard in the corner. And if he notices someone isn't being polite, he sort of says, right, everybody out, we need to restart. And finally, send telemetry. So hopefully from the demo, you remember the disky, and it could sort of show you 3 different numbers, and it had some lights, and that's good enough for the astronauts. But Houston needed more information. So the computer would constantly radio information about the landing. So it would transmit sort of where it was and how fast it was going, and what it was going to do next, what program it was in. All sorts of information. And then in Houston, there was a whole team of people like me staring at this data coming from the spaceship and making sure that the computer was working correctly. Lovely. So those are our 6 design principles. Use a high-level language so that complicated software is easy to implement. Divide your system into jobs where each job does one thing. If a job fails, then restart it, and hopefully whatever caused the failure will have gone away and the system will recover. checkpoint your good state, sort of save your working so that if you get restarted, you can pick back up where you left off. Hardware monitors the software to make sure that all the software is sort of getting along nicely, and send telemetry about your system to a group of experts who can make sure that it's working correctly. Well, I'm just going to have a quick cup of tea because that was very intense section of the talk, especially when giving it remotely. Now, the final section. When I first heard about these program alarms, 4 questions came into my head. First, kind of obviously, well, what caused them? What's all this about? What's all this 1202 stuff? And then, was the spacecraft in danger? This is obviously very important. And then there's this kind of thing as an engineer, it's sort of like, why did the alarms start halfway through the landing rather than at the start? If the alarms had happened at the start, everyone would have had so much more time to sort of decide whether it was okay or not. But of course, life doesn't work that way. The alarm started halfway through the landing at the most inconvenient time. And why was that? And finally, why did the alarm stop after Armstrong seized manual control? And over the next 10 minutes, you'll have a sort of a good working answer to all of these 4 questions, and you can impress all your friends. So firstly, I have lied to you. There was an extra radar on the spacecraft called the rendezvous radar. Now, the rendezvous radar was completely useless during landing, but when you were taking off again, that was when the rendezvous radar was useful. Now, during the landing, if you remember from the demo, the computer's doing all sorts of things. It's got the desired landing site and where it thinks it's going to land, and it's like steering the spacecraft and controlling the rocket engine, and it's a very computationally intensive part of the mission. And so the landing puts the computer under an 80% load. And the rendezvous radar had a hardware bug. And if you were really, really, really unlucky, you could trigger this hardware bug. And of course, on Apollo 11, in this context, they were really, really unlucky, and they hit this hardware bug. And the hardware bug meant that the rendezvous radar sent a stream of useless data to the computer. It wasn't meant to, because they were landing, they weren't taking off. It wasn't supposed to send any data, but they hit this bug. They were really unlucky, and the radar sent this constant stream of data. And that put the computer under an extra 15% load because the computer had to deal with all of this useless data. But this is fine. 80 plus 15 is 95%. So the computer is very heavily loaded, but it's not overloaded. And so this means that at the start of the landing, they didn't realize there was a problem. They had this hardware bug, but they didn't realize it had happened because the computer was still able to cope with the load. So what changed? Well, what changed was Buzz Aldrin. And Buzz Aldrin reached over to the diskey halfway through the landing, and he typed in verb 16, noun 68. Now, verb 16, this was a completely legitimate thing to do. He'd done it in training thousands of times before. He'd never had a problem with doing this on the computer. Verb 16, noun 68 means please show me some information about the landing and please constantly update the display. And like I said, this was a completely legitimate thing for Buzz to ask for. But internally, what happened was this. When Buzz typed in verb 16, noun 68, that started a new bit of code, and that code would calculate those numbers and it would put them on the diskey, and that code was running again and again because it was sort of constantly updating the display with that information. And that put the computer under an extra 10% load. Now, when you combine all 3 things all three of these tasks together, suddenly you have a problem. The computer is now under about 105% load, so it's overloaded. And it falls over in slow motion like this. The jobs very slowly pile up. And because the computer is overloaded, it can't quite dispatch them quickly enough. So when it comes to scheduling the 8th job that should never happen, there's a problem. There's no memory for job number 8. And that triggers that 1202 program alarm. What does Buzz see? Well, Buzz types in verb 16, noun 68, and he's looking at the disky, and presumably he's also looking at the moon and getting very excited. And then he sees two lights that you never want to see when you're landing on the moon. First is the program alarm light, followed rapidly by the restart light. Buzz at this point, I'm sure, takes a big gulp. He needs to diagnose these program alarms. So he enters verb 5, noun 9, and the computer responds, and it says that a 1202 alarm has occurred. However, the spacecraft keeps on flying, and this is the miraculous bit. This is the real power of the computer. So here's the situation we were in. There's that extra 10% load. The program alarm happens, and the computer restarts bits of the software, but it does not restart that Buzz's verb 16, noun 68. That removes the overload from the computer and allows the spacecraft to keep on flying. So that's the first program alarm. So what about the second one? Well, Buzz, I'm sure, is slightly irritated. He's typed in verb 16, noun 68, and all that's happened is the computer's crashed. So he does what any self-respecting computer user would do. He types it in again. So he types in verb 16, noun 68 again. The same thing happens. The computer starts this extra bit of code that overloads the computer. The jobs pile up. There's no room for job number 8. That triggers the second program alarm. Once again, the computer restarts various jobs. It does not restart Buzz's verb 16, noun 68, and the system recovers. So that's the second program alarm. And you can hear on the mission recording, Buzz, he says, it seems to happen when we have a 1668 come up. So Buzz realizes correctly that when he's typing this in, that causes the computer to crash. He doesn't know why, but he realizes that's the connection. So let's just go back to our questions. What caused the program alarms? Well, you had this extra load from the rendezvous radar. And when you combine that with Buzz's completely legitimate verb 16, noun 68, that overloaded the computer and caused those alarms. Was the spacecraft in danger? No, the critical software kept on running the whole time. And why did the alarm start halfway through the landing rather than at the start? Well, if you remember, originally we had that hardware bug and the baseline load, and that wasn't enough to overload the computer. The straw that broke the camel's back was when Buzz typed in verb 16, noun 68. Okay, but there were 5 program alarms in total. So what about the other 3? Was that Buzz as well? No, I can absolutely assure you Buzz was sat on his hands. There was no way he was going to type in verb 16, noun 68 again. He wasn't going to risk it. No, the last 3 alarms happened much later in the flight during program 64. If you remember, that's where the computer's calculating that imaginary red dot and Armstrong can change the landing site with his hand controller. And that is just naturally more computationally intensive. So those guidance algorithms take up even more processing power. And when you combine that with the hardware bug, the computer just overloads itself without Buzz doing anything. So the increase in load from program 64 causes those final 3 alarms. But there's one final mystery. Why was it that when Armstrong seized manual control, why did the alarms stop? Of course, we're all very thankful that they did, because even though the spaceship was still flying, the alarms were very distracting, and the last thing you want is to be distracted when you're trying to touch down gently on the moon. So why did they stop? Well, we know what happened. He didn't take manual control at all. He entered program 66. And when you enter program 66, if you remember, the hand controller disconnects from those sophisticated algorithms, and it connects to the much lower level steering software. And that just reduces the load on the computer all by itself. And so the computer is now able to cope again, and that's why no more program alarms were seen. So if we go back to our questions, the cause for 3, 4, and 5, it was caused by the extra load from program 64. And the reason why they stopped was when Armstrong entered program 66, the load on the computer just reduced. Bringing this talk to a close, let's look at our design principles and see how they helped. Restart on failure. The computer was able to recover from Buzz typing in verb 16, noun 68 by restarting bits of the software and by not restarting things that were not important enough. And that helped the system to recover. Checkpoint your good state. So even though bits of the software were being restarted, the sort of critical information was always intact. So after the software restarted, it would look at its checkpoint and it would say, what am I doing? And the checkpoint would say, you're landing on the moon, this is where you're going to land, and this is how fast you're going, and this is where you are. And that allowed the software to pick back up where it left off. Send telemetry. Even Buzz diagnosing the program alarm with the diski was a real faff, but because telemetry was being sent back to Houston, that gave Houston the confidence and the authority to give Armstrong the go to continue. Now, I always like to bring people into my talks, because at the end of the day, these systems are created and used by people. The first person I want to talk about is Steve Bales. He accepted the NASA Group Achievement Award on behalf of the entire mission operations team. This is an incredibly prestigious internal award. In the words of Nixon, this is the young man when the computers seemed to be confused, and when he could have said stop, or when he could have said wait, said go. Steve Bales was the controller in mission control who gave Armstrong the go to continue. But it wasn't his decision alone. He was ably assisted by Jack Garman, a brilliant engineer in the back room. Jack Garman had a list of every single program alarm that could occur, and it was Jack Garman more than anyone else who understood these alarms, and he understood that the computer was still flying safely and that it was safe to continue. And finally, Margaret Hamilton. She led the team at MIT who developed this software, and she finally received the US Presidential Medal of Freedom in 2016. Margaret Hamilton basically spent her entire career sort of developing methods for creating fault-tolerant systems, like what I've been talking about today. So these techniques, which were really pioneering in the 60s, are the foundation of all sorts of robust software today. And the AGC's engineers created a system that I think they should be really proud of. It was pragmatic and realistic. It was done under huge time pressure and lots of feature creep. But the end result was very well thought through. And when the chips were down and when things didn't quite go as planned, the software performed brilliantly. So thank you very much for listening. And if there's time, I will very happily take any questions.
Would you like to, first of all, Robert, thank you very much for a fantastic talk. I particularly enjoyed your excellent graphics, which you've obviously worked on with great diligence and so on, fascinating. Would you like to make any comments about what we've been talking about was whatever we're talking, over 50 years ago. What is in simple terms, the difference between the sort of guidance systems they were using for the moon landing and what's been going on recently in Mars in a very sort of general sense?
So So the trade-offs are very different. So the computing power back then was very limited, and that meant that they were very limited in the sort of guidance calculations they would do. So, for example, there are various equations, for example, that describe the motion of a spacecraft around a moon, and there's the sort of really accurate equations, and there's the slightly less accurate equations, and sometimes they had to settle for the less accurate stuff because there wasn't enough power to use the really accurate stuff. So the technical trade-offs nowadays are there's much more computing power available, so these systems are in general more accurate, and they can do more themselves without any input from mission control. But the fundamental principles of how the software is designed, those 6 things that I listed, are completely the same today compared with 50 years ago.
Yeah, thank you. Yeah. I'm sure we're all thinking very almost putting ourselves in the driver's seat of that Apollo mission. I'm sure other questions will come on that one. It must have been absolutely terrifying to be in that position with all those warnings coming up and very quiet, careful thought going on. Yes, I sort of put myself in that position thanks to your explanation.
I think it's very important to remember that although I've described the excellent engineering that went into the computer, at the end of the day, it was the cool heads of the 2 astronauts more than anything else that saved the mission. I don't think anyone would dispute that.
But sorry, I was just going to say the equipment was basic, but obviously robust, and one sort of wonders in some way whether the greater complexity makes the chance of what should we say, makes it less easy for individuals to recover things in the way they obviously did with the Apollo mission.
I think that's a fair point.
Excuse me, you talked about the starting. How long does it actually take to do a restart?
So I think the question was, how long did it take to do a restart of the software? And it was really quick. So you know how like you restart your computer and it just takes ages? Well, the guidance computer wasn't like that. It took something like 2 seconds to restart. It was really, really quick.
Yeah, that is quick. Yeah.
Robert, thank you for a brilliant talk. Could you just tell us how you came by this information, which has been fascinating?
Yes. So I actually got into this on the 40th anniversary. That was 10 years ago. That's when I heard about the program alarms, and I read a really bad explanation about them that just didn't make sense. It was too simple, and I thought, well, I've got to get to the bottom of this. So thus started 10 years of me trying to drill down and understand in a bit more detail what exactly happened. And the really good thing about the Apollo guidance computer is that there's tens of thousands of pages of documentation available. So there's a real treasure trove of information if you look for it. And that's really unusual. Most of these other old computers that I'm interested in, there's maybe like 100 pages of information and that's it. But the AGC is really unique in that there's just this absolute treasure trove of information.
Catherine.
Yeah, my question was, the computer automatically restarted when there was the problem. First of all, could Houston have done anything through the telemetry, or would the astronaut have to, was there actually a manual switch that they would have had to have restarted if this automatic system hadn't occurred?
That is a great question that no one has ever asked. So, which is absolutely fantastic. I love it when I get new questions. So Houston couldn't, the astronauts could if they wanted to, but the software was very carefully designed, so it would always recognize if a problem had happened, and it would always trigger a restart itself. So you know, like your computer kind of goes a bit weird and then you have to restart it. That's not really the case with the AGC. The AGC was always smart enough to realize that it wasn't working properly, and it would restart itself.
Presumably, if it realized it had overrun its time slots and was running out of memory, then it knew it had to do something.
That's exactly right. But the computer also, I mean, I don't want to get too far into it, but for example, the computer would check all of the inputs to make sure that everything was kind of looking vaguely okay. And if the inputs got really awry, the computer would say, this doesn't look right, and it would restart itself. So it wasn't just overloads that it would detect all sorts of erroneous conditions.
Similar to Catherine's question, though, could the telemetry people down in Houston recognize what the root of the problem was? Could they see that the radar, the rendezvous radar, was feeding data in?
So right, so picture this, right? So the landing on the moon takes, I don't know, it's about 10 minutes from the start of the burn through to it touching down. And so during those 10 minutes, these program alarms occurred, and so the people in Houston, they knew there was an overload, but they didn't know why. But you can absolutely bet, as soon as they touched down on the surface, every engineer with any inkling of knowledge about this was phoned up, and they were asked to get to the bottom of this. And the reason why they were asked was because they were going to take off again, and they had to know whether the takeoff was going to go to plan or whether they had to take some mitigations. So all of the engineers were phoned up, and I was actually speaking to one of them a couple of weeks ago, and he said that within about a day, they put the pieces together and they realized what the problem was. So they didn't know in real time when the landing was happening that it was the radar, but about a day later, they'd sort of puzzled everything together and they'd worked out that was the problem. Here's a slightly controversial point. So I've been told that they knew about the hardware bug, and they basically knew it would happen 1 in a million times. Like they calculated that it would happen 1 in a million times, and they basically sort of crossed their fingers and hoped it wouldn't happen. And of course, once it did happen, they were then told to put in mitigations in future missions.
Well, presumably it's fairly straightforward to say, well, if you're in P63 or 64 or 66, then disconnect the radar.
Yeah. So so in the end, there was basically the astronaut. There's it's a little complicated. There's a switch that basically controls whether the radar data goes to the computer, and the astronauts on subsequent missions, they were told, like, whatever you do, make sure this switch is kind of off, so that you don't hit this problem. It's a little more complicated than that, but fundamentally the astronauts were told, like, make sure this switch is in the right position.
Unplug that radar and plug that one in, and then
yeah,
when
exactly.
you take off, it's the other way around.
Exactly right. Yes, you're totally right.
Robert, was that the only bug in the system? I can't believe that was the only bug they actually had. Were there other bugs in other parts of the system? Anyone you mentioned, of course.
Oh, do you know, that's a good question as well.
That's a nasty question. Nobody's talked about them because there was no evidence.
So I'm just thinking, if there are 1 million bugs and they're all 1 million to 1, there's a pretty good chance one of them's going to happen. In fact, almost a certainty.
So
there wouldn't be 1 million.
So
No.
I'm not aware of any other software issues that they encountered. Obviously, all software has limitations that you work around. What I would say is, like, the fundamental thrust of my talk is that software will have bugs, and so you, rather than fight it, you accept it, and then you design your system so it within reason it can cope even when a bug occurs.
Yeah, thank you.
Did they have things like failure mode and effects analysis and those sort of tools for planning and envisaging what could go wrong?
I don't know precisely what analysis techniques they used. My understanding is in the early 60s, a lot of this stuff just didn't exist. I know that Margaret Hamilton in particular, I mentioned she kind of dedicated a lot of her career to developing these robust systems. And so I think over time, she and others kind of developed some of these analysis techniques. But I don't know how much of it was used in Apollo itself.
Right, we got any other questions? If not, I'd like to thank you once again. Yes, sorry.
If the American system had these bugs, what were the Russians doing?
They didn't have a computer like that, so they were all right.
So there's very little information about the Russian equivalent, although if you think about things like the Soyuz capsule, for example, which, as I understand it, manages its entire re-entry to Earth by itself, I think that's a phenomenal achievement in and of itself. So I'm sure a lot of the Russian stuff was similarly ingenious and is just less appreciated because less is known about it.
Thank you.
One thing I was wondering about, you gave the impression that when you started P63 and the moon was still some distance off, or your landing site was some distance off, that the rendezvous computer, well, the computer knew where it was going, but I presume in reality it knew roughly how high it was, or roughly where it was, but it was refining and improving as it got closer.
Yes, that's absolutely right. So at the start of P63, the data source was the IMU, but because you're subjecting the IMU to a huge amount of acceleration, and so you're in particular you're integrating. So what the IMU is doing is it's integrating acceleration to get velocity, and it's integrating velocity to get position. And we all know that if you integrate sort of large values, then you end up with a large error. And so that, amongst other things, did cause a big error, which is why it was so important to have the landing radar, because with the landing radar, there is no integration. It can measure the exact height, and it can use Doppler to measure the exact vertical speed. So the landing radar was really an essential source of accuracy, but it only kicked in halfway through the descent.
And it's only telling you altitude. It's not guiding you as to how far away you are from where you want to be until you can see it virtually.
Exactly right. Yeah. So the final system was kind of a blend of the two, plus Neil Armstrong's eyes, because he knew the surface of the moon better than anyone. So he was also looking out the window, and that's why you had P64, because it was recognised that the human eye could see the landing site, much better than a computer ever could.
Yeah, it looked like a very cunning way of combining the two together.
Yeah, definitely. And the interplay of the humans and the computer, and in my opinion, the fact that the whole is greater than the sum of those two parts, I think is just one of the most sort of glorious engineering achievements of computer science.
Not to mention the courage of actually doing it.
Yeah. And not forgetting the poor people who had to weave all of those programs with the little wires through the hoops. I mean, could you imagine doing that? My goodness.
Could I make a comment about NASA and software? I mean, I got interested in things they were doing in the 1980s when I was producing software for nuclear power stations. I mean, it was very clear in the 1980s is they had a bunch of people who were producing more reliable software than anybody else in the world. And they developed some really fairly straightforward techniques like check everything, get somebody else to check it and then check it again. And they actually did more with really quite basic principles like that than other people were doing with, so-called magic bullet techniques. They were just basically saying, understand what you're doing and check it, and one of they had this, what they call the software factory. And I think one of the sad things that happened in the 1990s is NASA went through this faster, better, cheaper reorganization. And all that was destroyed. It was all broken up and everything was contracted out. One of the next things that happened is they started crashing spacecraft into Mars. So I mean, there's a real lesson.
Yes. So so reflecting on that, two thoughts spring to mind. First of all, one would hope that software in charge of nuclear power was the absolute best in the world, because clearly the constraints there are it's incredibly important for the software to be right. Also, yes, so the AGC, the hardware and the software was developed by a very tight-knit team in a sort of collegiate atmosphere at MIT. And I don't want to sugarcoat this. This was a hard project. It was over time, it was late at times, and they were short of hardware and they struggled to build the hardware reliably enough. It was a very difficult project. I don't want to glamorize it, but it was done by this very close-knit and smart team of people. And I think when you distribute software out and you have big teams working on it, there's a huge challenge in making sure that people are talking to each other, and that everything is coming together exactly as you want it. And I think that's a big challenge as you scale software up and you contract it out.
Yes, that's, if I may say so, an interesting point. At the moment, I've got problems with a Microsoft program, and I've never had problems with Excel programs.
I thought you were going to say that.
I'm told that Microsoft have so many huge teams, they don't always work together. And maybe that's a lesson. They compete with each other, probably.
Well, of course, there is another famous book which dates from the 1960s called The Mythical Man Month, and I'm sure Robert knows about this. And it's about how adding more people to a project slows it down and makes it worse. So that was one of the great lessons of 1960s software engineering. And picking up the point about nuclear power and the relationship between hardware and software in the 1980s, when we were building Sizewell B, the reliability in the protection system came from the combination of having quite a sophisticated software protection system, but having hardware which backed it up. So, if it went outside certain parameters, the hardware would just shut everything down. And again, that was a way you could get really high levels of reliability.
Absolutely, and it's not quite the same, but you can see that with things like the AGC, where there is some hardware support for making sure the software is behaving, hardware detects overload. So yeah, it's not quite analogous, but again, you can kind of trace all this stuff back, and at the end of the day, it's software often does weird things, and it's much more difficult to argue with a chunk of metal doing something.
Presumably they didn't call it a watchdog then.
It was, you had a primary protection system, that was the hardware. That would just cut everything, and secondary protection system was a bit more careful with the managing the plants. You want to manage plant. There are times when you just need to shut something down, and other times where you want to shut things down gracefully so you don't actually cause damage while you're shutting things down. Just turning everything off immediately isn't good in general. You get big thermal transients. So those are the sorts of balances you sometimes have to deal with. Of course, things have moved on in the last 20 or 30 years as well. everything is much more software centered these days.
My one reflection, and this is not supposed to sound flippant, is that you don't have to fly a nuclear power station. So although the safety margin you need and the level of reliability is even higher than something like spaceflight, you don't have the same design constraints in terms of only being able to ship 1 cubic foot of space with 35 watts of power and 32 kilograms.
Absolutely.
Like, you would not believe, like, the hardware engineers for the AGC, if they could have had 0.1 more of a cubic foot on their Christmas list, they absolutely would have, and there was no way that they could. So I think both domains, it's really impressive what is achieved with the kind of design constraints that both sets of engineers are under.
But in the 1980s, certainly when I started doing this stuff, I joined in 76. Really into the 1980s, nuclear power stations were being, we had PDP 11 computers. 16-bit computers with very limited amounts of memory and disk space and so on, because they were so damn reliable.
Yeah.
Right, Malcolm, do you want to say anything for speaker?
Yes, well, we certainly went out with a bang this year with a superb lecture. Thank you very much, Robert, for that. That was really great. Even I understood it, so you did very well.